So in the previous discussion, we had a fully model-free inversion approach based on measurements of the Stokes vector for the double the frequency, and then pooling those measurements to invert and recover the local frame Mueller tensor. What we're going to do now is explore some additional simplifications that can arise by considering explicit models for the depolarization. And we're going to start in this one considering a purely depolarized measurement, where you scramble the polarization state of the light coming in, it generates second harmonic generation, and then you scramble the polarization state of the light coming out. Now, I'm not saying that all of the light is scrambled coming in and all of the light is scrambled coming out. I am saying now, however, that the depolarized component is assumed to be arising from that combination of scattering. So in other words, you get a completely flat polarization independent contribution to the background from depolarized SHG in combination with a nice cleanly polarized SHG, and your net measurement is a linear combination of those two contributions. So that's what we'll be considering here. What we're going to be doing is first seeing how this plays out in terms of the Mueller tensor, and then relating this back to some simple measurements in terms of classical architectures for doing polarization analysis. So if we want to consider complete depolarization, then that means that the background contribution in this for this particular model is independent of both the incident and detected polarization states. And that means that you have, so if you have something that is independent of the detected polarization state, then that means that the first index is just given by the sum of the two in frequencies, and all the other ones, the IH plus IV, all the other ones, IH minus IV, IR minus IL, I plus 45 minus I minus 45, all of those are going to be zero valued if the second harmonic light is completely depolarized, at least the component of the light that we're considering in this depolarized model. So we know that the first entry must be zero. That'd be the only non-zero. So whatever we have for M for the Mueller tensor describing the depolarized component, we know that the first index must be zero because the double light has no polarization, is depolarized for the depolarized component. All right. The other two terms also have to be zero valued because otherwise the conversion efficiency of this background SHG would also depend on the polarization state of the fundamental light. And in this model, it's completely independent of both. And so therefore, it's really a trivial simplification of the Mueller tensor describing the depolarized component. You only have one entry, and it's just the M000 entry. So it's a single, of the 64 possible elements, only one remains in this isotropically depolarized model. And again, we're going to be, well, not again. So we're going to have some scaling between the purely polarized component and the purely depolarized component. That scaling factor is given by alpha, this degree of depolarization. All right. So we can take advantage in the case of SHG, we can take advantage of some simplifications that arise by nature of the fact that it is a coherent process. And because it's a coherent process, the light that's coming off from the Jones component is purely polarized as long as our electric fields going in, driving it, are purely polarized. And assuming we are putting in, pure polarization states to drive this process, then it's actually pretty straightforward to pull out the component that's purely polarized by taking advantage of what's known as the degree of polarization. It's well established. I won't go into the details as to why. You can convince yourself of it. But if you've got something that has a high degree of polarization purity, for example, if something is purely polarized, then the degree of polarization approaches 1. And that is basically saying that these terms in the numerator describing the first, second, and third element in the Stokes vector squared and summed are the same magnitude as the sum of intensities. And so therefore that approaches a value of 1. If you have purely depolarized light, then S0 begins to be the only one that's significant and non-zero. All the things in the numerator go to 0 because they're all differences in intensity, and the degree of polarization is 0. So the fact that the DOP is 1 in the case of purely polarized light allows us to take whatever we measure and disentangle it into two different components. We can measure alpha directly from the degree of polarization if we're doing Stokes vector measurements for the doubled frequency. And if we know alpha from the degree of polarization, then we can just plug it in, and it becomes very easy to model and invert this. And forget this is here. This is something you'll see later on. So if you know alpha, then it's pretty easy to invert that problem. So we're going to consider a very common measurement platform, one in which we're detecting horizontally or vertically polarized light as a function of the polarization state of light coming in. And it's shown here as a continuous property as a function of some angle gamma. But this could also, depending on your particular angle and value of gamma, you can also get the pure vertical, pure horizontal, pure +4, -45. All of that comes depending on the individual selections of gamma. If we let gamma be a continuous parameter and measure the intensity here, for example, the horizontal detector as a function of gamma, well, then it turns out there's really only 5 parameters we can back out. And these are the terms here. These are all the harmonics of gamma. So these 5 coefficients will correspond to the set of observables in terms of the intensity that can be recovered on the horizontal detector. And of course, there's another set of analogous 5 parameters on the vertical detector. So measuring the intensity as a function of gamma gives us 10 parameters that are tied back to these tensor elements. And I'm going through all of this very quickly because that's really discussed in greater detail in the section on the Jones tensor measurements and nose microscopy, so I won't belabor the point right here. Building on that previous framework, we know how to describe the purely polarized component of the signal, and we can relate that all the way, if we want to, back to the molecular response, the individual molecules contributing to the hyperpolarizability. These might be individual fibrils in the case of second harmonic generation from collagen, or if there's some dye inside a membrane, it might be the chromophores embedded within the membrane. And then we can relate those back to the local frame response by, this is the symmetry matrix. It serves the same role as Q for the Mueller tensor, populating the full set of elements from the smaller subset of symmetry allowed elements. R is an orientational average. I'm going again through this very quickly because this is all rehashed from other presentations. L, local field correction factors. J, this is all for describing the purely polarized component using the established descriptions based on the previous lectures. And the one interesting wrinkle is this part right here, the depolarized component. And what does A, this coefficient of 10 parameters, what does that look like for the depolarized light? And it turns out that it's actually not hard to show. If you just go through those assumptions, apply the Mueller operations, and then propagate all the way through to generate what A should be, it has this form. So this would be the horizontal detector, and this would be the vertical detector, 2 stacked sets of 5 elements. And so it's fairly straightforward to disentangle those 2 contributions. If you know A, for example, from degree of depolarization measurements or from linear scattering measurements, then you can essentially subtract this off when solving for whatever properties you want to solve for, either information on the molecular tensor or information on the orientation distribution in the local frame. And that's a good place to stop.